Chapter 5. Operating Strength Limitations. The weight of the structural components of an aircraft is an extremely important factor in the development of an efficient aircraft configuration. In no other field of mechanical design is there such necessary importance assigned to structural weight. The efficient aircraft and powerplant structure is the zenith of highly refined, minimum weight design. In order to obtain the required service life from his aircraft, the naval aviator must understand, appreciate, and observe the operating strength limitations. Failure to do so will incur excessive maintenance costs and a high incidence of failure during the service life of an aircraft. General definitions and structural requirements. There are strength requirements which are common to all aircraft. In general, these requirements can be separated into three particular areas. These are detailed in the following discussion. Static strength. The static strength requirement is the consideration given to the effect of simple static loads with none of the ramifications of the repetition or cyclic variation of loads. An important reference point in the static strength requirement is the limit load condition. When the aircraft is at the design configuration, there will be some maximum of load which would be anticipated from the mission requirement of the airplane. For example, a fighter or attack-type aircraft, at the design configuration, may encounter a very peak load factor of 7.5 in the accomplishment of its mission. Of course, such an aircraft may be subject to load factors of 3, 4, 5, 6, 1, etc., but no more than 7.5 should be required to accomplish the mission. Thus, the limit load condition is the maximum of loads anticipated in normal operation of the aircraft. Various types of aircraft will have different limit load factors according to the primary mission of the aircraft. Typical values are tabulated below. Fighter or attack aircraft, positive limit load factor 7.5. Trainer aircraft, positive limit load factor 7.5. Transport, patrol, or anti-submarine aircraft, positive limit load factor 3.0 or 2.5. Of course, these examples are quite general, and it is important to note that there may be variations according to specific mission requirements. Since the limit load is the maximum of the normally anticipated loads, the aircraft structure must withstand this load with no ill effects. Specifically, the primary structure of the aircraft should experience no objectionable permanent deformation when subjected to the limit load. In fact, the components must withstand this load with a positive margin. This requirement implies that the aircraft should withstand successfully the limit load and then return to the original unstressed shape when the load is removed. Obviously, if the aircraft is subjected to some load which is in excess of the limit load, the overstress may incur an objectionable permanent deformation of the primary structure and require replacement of the damaged parts. Many different flight and ground load conditions must be considered to define the most critical conditions for the structural components. In addition to positive lift flight, negative lift flight must be considered. Also, the effect of flap and landing gear configuration, gross weight, flight Mach number, symmetry of loading, CG positions, etc., must be studied to account for all possible sources of critical loads. To verify the capability of the structure, ground static tests are conducted, and flight demonstrations are required. To provide for the rare instances of flight when a load greater than the limit is required to prevent a disaster, an ultimate factor of safety is provided. Experience has shown that an ultimate factor of safety of 1.5 is sufficient for piloted aircraft. Thus, the aircraft must be capable of withstanding a load which is 1.5 times the design limit load. The primary structure of the aircraft must withstand the ultimate load, 1.5 times the limit load, without failure. Of course, permanent deformation may be expected with this overstress, but no actual failure of the major load-carrying components should take place at ultimate load. Ground static tests are necessary to verify this capability of the structure. An appreciation of the static strength requirements may be obtained by inspection of the basic properties of a typical aircraft metal. Figure 3.1 illustrates the typical static strength properties of a metal sample by a plot of applied stress versus resulting strain. At low values of stress, the plot of stress and strain is essentially a straight line, i.e., the material in this range is elastic. A stress applied in this range incurs no permanent deformation, and the material returns to the original unstressed shape when the stress is released. At higher values of stress, the plot of stress versus strain develops a distinct curvature in the strain direction, and the material incurs disproportionate strains. High levels of stress applied to the part and then released produce a permanent deformation. Upon release of some high stress, the metal snaps back but not all the way. The stress defining the limit of tolerable permanent strain is the yield stress, and stresses applied above this point produce objectionable permanent deformation. The very highest stress the material can withstand is the ultimate stress. Noticeable permanent deformation usually occurs in this range, but the material does have the capability for withstanding one application of the ultimate stress. The relationship between the stress-strain diagram and operating strength limits should be obvious. If the aircraft is subjected to a load greater than the limit, the yield stress may be exceeded, and objectionable permanent deformation may result. If the aircraft is subject to a load greater than the ultimate, failure is imminent. Service life. The various components of the aircraft and powerplant structure must be capable of operating without failure or excessive deformation throughout the intended service life. The repetition of various service loads can produce fatigue damage in the structure, and special attention must be given to prevent fatigue failure within the service life. Also, the sustaining of various service loads can produce creep damage, and special attention must be given to prevent excessive deformation or creep failure within the service life. This is a particular feature of components which are subjected to operation at high temperatures. Fatigue considerations. The fatigue strength requirement is the consideration given the cumulative effect of repeated or cyclic loads during service. While there is a vague relationship with the static strength, repeated cyclic loads produce a completely separate effect. If a cyclic, tensile stress is applied to a metal sample, the part is subject to a fatigue-type loading. After a period of time, the cyclic stressing will produce a minute crack at some critical location in the sample. With continued application of the varying stress, the crack will enlarge and propagate into the cross-section. When the crack has progressed sufficiently, the remaining cross-section is incapable of withstanding the imposed stress and a sudden, final rupture occurs. In this fashion, a metal can be failed at stresses much lower than the static ultimate strength. Of course, the time necessary to produce fatigue failure is related to the magnitude of the cyclic stress. This relationship is typified by the graph of Figure 5.1. The fatigue strength of a material can be demonstrated by a plot of cyclic stress versus cycles of stress required to produce fatigue failure. As might be expected, a very high stress level requires relatively few cycles to produce fatigue failure. Moderate stress levels require a fairly large number of cycles to produce failure, and a very low stress may require nearly an infinite number of cycles to produce failure. The very certain implication is that the aircraft must be capable of withstanding the gamut of service loads without producing fatigue failure of the primary structure. For each mission type of aircraft, there is a probable spectrum of loads which the aircraft will encounter. That is, various loads will be encountered with a frequency particular to the mission profile. The fighter or attack type of aircraft usually experiences a predominance of maneuver loads, while the transport or patrol type usually encounters a predominance of gust loads. Since fatigue damage is cumulative during cyclic stressing, the useful service life of the aircraft must be anticipated to predict the gross effect of service loads. Then, the primary structure is required to sustain the typical load spectrum through the anticipated service life without the occurrence of fatigue failure. To prove this capability of the structure, various major components must be subjected to an accelerated fatigue test to verify the resistance to repeated loads. The design of a highly stressed or long-life structure emphasizes the problems of fatigue. Great care must be taken during design and manufacture to minimize stress concentrations which enhance fatigue. When the aircraft enters service operation, care must be taken in the maintenance of components to ensure proper adjustment, torquing, inspection, etc., as proper maintenance is a necessity for achieving full service life. Also, the structure must not be subjected to a load spectrum more severe than was considered in design, or fatigue failures may occur within the anticipated service life. With this additional factor in mind, any pilot should have all the more respect for the operating strength limits. Recurring overstress causes a high rate of fatigue damage. There are many examples of the detrimental effect of repeated overstress on service life. One major automobile manufacturer advertised his product as guaranteed to provide 100,000 miles of normal driving without mechanical failure. The little old lady from Pasadena, the original owner of all used cars, will probably best the guaranteed mileage by many times. On the other hand, the hot rod artist and freeway Grand Prix contender do not qualify for the guarantee, since their manner of operation could not be considered normal. The typical modern automobile may be capable of 60,000 to 100,000 miles of normal operation before an overhaul is necessary. However, this same automobile may encounter catastrophic failures in a few hundred miles if operated continually at maximum torque in low drive range. Obviously, there are similar relationships for aircraft and powerplant structures. Creep considerations. By definition, creep is the structural deformation which occurs as a function of time. If a part is subjected to a constant stress of sufficient magnitude, the part will continue to develop plastic strain and deform with time. Eventually, failure can occur from the accumulation of creep damage. Creep conditions are most critical at high stress and high temperature, since both factors increase the rate of creep damage. Of course, any structure subject to creep conditions should not encounter excessive deformation or failure within the anticipated service life. The high operating temperatures of gas turbine components furnish a critical environment for creep conditions. The normal operating temperatures and stresses of gas turbine components create considerable problems in design for service life. Thus, operating limitations deserve very serious respect, since excessive engine speed or excessive turbine temperatures will cause a large increase in the rate of creep damage and lead to premature failure of components. Gas turbines require high operating temperatures to achieve high performance and efficiency, and short periods of excessive temperatures can incur highly damaging creep rates. Airplane structures can be subject to high temperatures due to aerodynamic heating at high Mach numbers. Thus, very high-speed airplanes can be subject to operating limitations due to creep conditions. Aeroelastic effects. The requirement for structural stiffness and rigidity is the consideration given to the interaction of aerodynamic forces and deflections of the structure. The aircraft and its components must have sufficient stiffness to prevent or minimize aeroelastic influences in the normal flight range. Aileron reversal, divergence, flutter, and vibration should not occur in the range of flight speeds which will be normal operation for the aircraft. It is important to distinguish between strength and stiffness. Strength is simply the resistance to load, while stiffness is the resistance to deflection or deformation. While strength and stiffness are related, it is necessary to appreciate that adequate structural strength does not automatically provide adequate stiffness. Thus, special consideration is necessary to provide the structural components with specific stiffness characteristics to prevent undesirable aeroelastic effects during normal operation. An obvious solution to the apparent problems of static strength, fatigue strength, stiffness, and rigidity would be to build the airplane like a product of an anvil works, capable of withstanding all conceivable loads. However, high-performance airplane configurations cannot be developed with inefficient, lowly stressed structures. The effect of additional weight is best illustrated by preliminary design studies of a very long-range, high-altitude bomber. In the preliminary phases of design, each additional pound of any weight would necessitate a 25-pound increase in gross weight to maintain the same performance. An increase in the weight of any item produces a chain reaction. More fuel, larger tanks, bigger engines, more fuel, heavier landing gear, more fuel, etc. In the competitive sense of design, no additional structural weight can be tolerated to provide more strength than is specified as necessary for the design mission requirement. Aircraft loads and operating limitations. Flight loads. Maneuvers and gusts. The loads imposed on an aircraft in flight are the result of maneuvers and gusts. The maneuver loads may predominate in the design of fighter airplanes, while gust loads may predominate in the design of large, multi-engine aircraft. The maneuver loads an airplane may encounter depend in great part on the mission type of the airplane. However, the maximum maneuvering capability is of interest because of the relationship with strength limits. The flight load factor is defined as the proportion between airplane lift and weight, where lowercase n equals L over W, or lowercase n equals load factor, L equals lift in pounds, and W equals weight in pounds. Maneuvering load factors. The maximum lift attainable at any airspeed occurs when the airplane is at capital CL max. With the use of the basic lift equation, this maximum lift is expressed as L max equals capital CL max times 1 half lowercase rho v squared times capital S. Since maximum lift must be equal to the weight at the stall speed, W equals capital CL max times 1 half lowercase rho v s squared times capital S. If the effects of compressibility and viscosity on capital CL max are neglected for simplification, the maximum load factor attainable is determined by the following relationship. Lowercase n max equals L max over W, or lowercase n max equals capital CL max times 1 half lowercase rho v squared times capital S over capital CL max times 1 half lowercase rho v s squared times capital S, or lowercase n max equals the quantity v over vs squared. Thus, if the airplane is flying at twice the stall speed, and the angle of attack is increased to obtain maximum lift, a maximum load factor of 4 will result. At 3 times the stall speed, 9 Gs would result. 4 times the stall speed, 16 Gs result. 5 times the stall speed, 25 Gs result, etc. Therefore, any airplane which has high speed performance may have the capability of high maneuvering load factors. The airplane which is capable of flight speeds that are many times the stall speed will require due consideration of the operating strength limits. The structural design of the aircraft must consider the possibility of negative load factors from maneuvers. Since the pilot cannot comfortably tolerate large prolonged negative G, the aircraft need not be designed for negative load factors as great as the positive load factors. The effect of airplane gross weight during maneuvers must be appreciated because of the particular relation to flight operating strength limitations. During flight, the pilot appreciates the degree of a maneuver from the inertia forces produced by various load factors. The airplane structure senses the degree of a maneuver principally by the air loads involved. Thus, the pilot recognizes load factor while the structure recognizes only load. To better understand this relationship, consider an example airplane whose basic configuration gross weight is 20,000 pounds. At this basic configuration, assume a limit load factor for symmetrical flight of 5.6 and an ultimate load factor of 8.4. If the airplane is operated at any other configuration, the load factor limits will be altered. The following data illustrate this fact by tabulating the load factors required to produce identical air loads at various gross weights. Gross weight, 20,000 pounds, basic. Limit load factor, 5.60. Ultimate load factor, 8.40. Gross weight, 30,000 pounds, max takeoff. Limit load factor, 3.73. Ultimate load factor, 5.60. Gross weight, 13,333, minimum fuel. Limit load factor, 8.40. Ultimate load factor, 12.60. As illustrated, at high gross weights above the basic configuration weight, the limit and ultimate load factors may be seriously reduced. For the airplane shown, a 5G maneuver immediately after a high gross weight takeoff could be very near the disaster regime, especially if turbulence is associated with the maneuver. In the same sense, this airplane at very low operating weights below that of the basic configuration would experience greatly increased limit and ultimate load factors. Operation in this region of high load factors at low gross weight may create the impression that the airplane has great excess strength capability. This effect must be understood and intelligently appreciated, since it is not uncommon to have a modern airplane configuration with more than 50% of its gross weight as fuel. Gust load factors. Gusts are associated with the vertical and horizontal velocity gradients in the atmosphere. A horizontal gust produces a change in dynamic pressure on the airplane, but causes relatively small and unimportant changes in flight load factor. The more important gusts are the vertical gusts, which cause changes in angle of attack. This process is illustrated in Figure 5.2. The vectorial addition of the gust velocity to the airplane velocity causes the change in angle of attack and change in lift. The change in angle of attack at some flight condition causes a change in the flight load factor. The increment change in load factor due to the vertical gust can be determined from the following equation. Delta lowercase n equals 0.115 times lowercase m times the square root of lowercase sigma over W over capital S times V sub e times Ku, where delta lowercase n equals change in load factor due to gusts. Lowercase m equals lift curve slope in units of capital CL per degree of lowercase alpha. Lowercase sigma equals Altitude density ratio. W over capital S equals wing loading in pounds per square foot. V sub E equals equivalent airspeed in knots. And Ku equals equivalent sharp-edged gust velocity in feet per second. As an example, consider the case of an airplane with a lift curve slope, lowercase m, equals 0.08, and wing loading, or W over capital S, equals 60 pounds per square foot. If this airplane were flying at sea level at 350 knots and encountered an effective gust of 30 feet per second, the gust would produce a load factor increment of 1.61. This increment would be added to the flight load factor of the airplane prior to the gust, e.g., if in level flight before encountering the gust, a final load factor of 1.0 plus 1.61 equals 2.61 would result. As a general requirement, all airplanes must be capable of withstanding an approximate effective plus or minus 30 feet per second gust when at maximum level flight speed for normal rated power. Such a gust intensity has relatively low frequency of occurrence in ordinary flying operations. The equation for gust load increment provides a basis for appreciating many of the variables of flight. The gust load increment varies directly with the equivalent sharp-edged gust velocity, Ku, since this factor affects the change in angle of attack. The highest reasonable gust velocity that may be anticipated is an actual vertical velocity, U, of 50 feet per second. This value is tempered by the fact that the airplane does not effectively encounter the full effect because of the response of the airplane and the gradient of the gust. A gust factor, K, usually on the order of 0.6, reduces the actual gust to the equivalent sharp-edged gust velocity, Ku. The properties of the airplane exert a powerful influence on the gust increment. The lift curve slope, lowercase m, relates the sensitivity of the airplane to changes in angle of attack. An aircraft with a straight, high aspect ratio wing would have a high lift curve slope, and would be quite sensitive to gusts. On the other hand, the low aspect ratio, swept wing airplane has a low lift curve slope, and is comparatively less sensitive to turbulence. The apparent effect of wing loading, W over capital S, is at times misleading, and is best understood by considering a particular airplane encountering a fixed gust condition at various gross weights. If the airplane encounters the gust at lower than ordinary gross weight, the accelerations due to the gust condition are higher. This is explained by the fact that, essentially, the same lift change acts on the lighter mass. The high accelerations and inertia forces magnify the impression of the magnitude of turbulence. If this same airplane encounters the gust condition at higher than ordinary gross weight, the accelerations due to the gust condition are lower, i.e., the same lift change acts on the greatest mass. Since the pilot primarily senses the degree of turbulence by the resulting accelerations and inertia forces, this effect can produce a very misleading impression. The effect of airspeed and altitude on the gust load factor is important from the standpoint of flying operations. The effect of altitude is related by the term square root lowercase sigma, which relates that an airplane flying at a given EAS at 40,000 feet, lowercase sigma, equals 0.25, would experience a gust load factor increment only 1/2 as great as at sea level. This effect results because the true airspeed is twice as great, and only 1/2 the change in angle of attack occurs for a given gust velocity. The effect of airspeed is illustrated by the linear variation of gust increment with equivalent airspeed. Such a variation emphasizes the effect of gusts at high flight speeds, and the probability of structural damage at excessive speeds in turbulence. The operation of any aircraft is subject to specific operating strength limitations. A single large overstress may cause structural failure or damage severe enough to require costly overhaul. Less severe overstress repeated for sufficient time will cause fatigue cracking and require replacement of parts to prevent subsequent failure. A combat airplane need not be operated in a manner like the little old lady from Pasadena, driving to church on Sunday, but each aircraft type has strength capability only specific to the mission requirement. Operating limitations must be given due regard. The VN, or VG, diagram. The operating flight strength limitations of an airplane are presented in the form of a VN or VG diagram. This chart usually is included in the aircraft flight handbook in the section dealing with operating limitations. A typical VN diagram is shown in Figure 5.3. The VN diagram presented in Figure 5.3 is intended to present the most important general features of such a diagram and does not necessarily represent the characteristics of any particular airplane. Each airplane type has its own particular V-end diagram with specific V's and N's. The flight operating strength of an airplane is presented on a graph whose horizontal scale is airspeed, V, and vertical scale is load factor, lowercase n. The presentation of the airplane strength is contingent on 4 factors being known. 1. The aircraft gross weight. 2. The configuration of the aircraft, clean, external stores, flaps and landing gear position, etc. 3. Symmetry of loading, since a rolling pull-out at high speed can reduce the structural limits to approximately 2/3 of the symmetrical load limits, and 4. The applicable altitude. A change in any one of these 4 factors can cause important changes in operating limits. For the airplane shown, the positive limit load factor is 7.5, and the positive ultimate load factor is 11.25. 7.5 times 1.5. For negative lift flight conditions, the negative limit load factor is 3.0, and the negative ultimate load factor is 4.5. 3.0 times 1.5. The limit airspeed is stated as 575 knots while the wing level stall speed is apparently 100 knots. Figure 5.4 provides supplementary information to illustrate the significance of the V-end diagram of Figure 5.3. The lines of maximum lift capability are the first points of importance on the V-end diagram. The subject aircraft is capable of developing no more than one positive G at 100 knots, the wing level stall speed of the airplane. Since the maximum load factor varies with the square of the airspeed, the maximum positive lift capability of this airplane is 4 Gs at 200 knots, 9 Gs at 300 knots, 16 Gs at 400 knots, etc. Any load factor above this line is unavailable aerodynamically, i.e., the subject airplane cannot fly above the line of maximum lift capability. Essentially the same situation exists for negative lift flight with the exception that the speed necessary to produce a given negative load factor is higher than that to produce the same positive load factor. Generally, the negative CL max is less than the positive CL max, and the airplane may lack sufficient control power to maneuver in this direction. If the subject airplane is flown at a positive load factor greater than the positive limit load factor of 7.5, structural damage will be possible. When the airplane is operated in this region, objectionable permanent deformation of the primary structure may take place, and a high rate of fatigue damage is incurred. Operation above the limit load factor must be avoided in normal operation. If conditions of extreme emergency require load factors above the limit to prevent an immediate disaster, the airplane should be capable of withstanding the ultimate load factor without failure. The same situation exists in negative lift flight with the exception that the limit and ultimate load factors are of smaller magnitude, and the negative limit load factor may not be the same value at all airspeeds. At speeds above the maximum level flight airspeed, the negative limit load factor may be of smaller magnitude. The limit airspeed, or redline speed, is a design reference point for the airplane. The subject airplane is limited to 575 knots. If flight is attempted beyond the limit airspeed, structural damage or structural failure may result from a variety of phenomena. The airplane in flight above the limit airspeed may encounter A. Critical gusts. B. Destructive flutter. C. Aileron reversal. D. Wing or surface divergence. E. Critical compressibility effects such as stability and control problems, damaging buffet, etc. The occurrence of any one of these items could cause structural damage or failure of the primary structure. A reasonable accounting of these items is required during the design of an airplane to prevent such occurrences in the required operating regions. The limit airspeed of an airplane may be any value between terminal dive speed and 1.2 times the maximum level flight speed, depending on the aircraft type and mission requirement. Whatever the resulting limit airspeed happens to be, it deserves due respect. Thus, the airplane in flight is limited to a regime of airspeeds and Gs which do not exceed the limit, or redline, speed, do not exceed the limit load factor, and cannot exceed the maximum lift capability. The airplane must be operated within this envelope to prevent structural damage and ensure that the anticipated service life of the airplane is obtained. The pilot must appreciate the V-end diagram as describing the allowable combination of airspeeds and load factors for safe operation. Any maneuver, gust, or gust plus maneuver outside the structural envelope can cause structural damage and effectively shorten the service life of the airplane. There are 2 points of great importance on the V-end diagram of Figure 5.4. Point B is the intersection of the negative limit load factor and line of maximum negative lift capability. Any airspeed greater than point B provides a negative lift capability sufficient to damage the airplane. Any airspeed less than point B does not provide negative lift capability sufficient to damage the airplane from excessive flight loads. Point A is the intersection of the positive limit load factor and the line of maximum positive lift capability. The airspeed at this point is the minimum airspeed at which the limit load can be developed aerodynamically. Any airspeed greater than point A provides a positive lift capability sufficient to damage the airplane. Any airspeed less than point A does not provide positive lift capability sufficient to cause damage from excessive flight loads. The usual term given to the speed at point A is the maneuvering speed, since consideration of subsonic aerodynamics would predict minimum usable turn radius to occur at this condition. The maneuvering speed is a valuable reference point, since an airplane operating below this point cannot produce a damaging positive flight load. Any combination of maneuver and gust cannot create damage due to excess air load when the airplane is below the maneuvering speed. The maneuvering speed can be computed from the following equation. VA equals VS times the square root of lowercase and limit, where VA equals maneuvering speed in knots, VS equals stall speed in knots, and, in limit, equals limit load factor. Of course, the stall speed and limit load factor must be appropriate for the airplane gross weight. One notable fact is that this speed, once properly computed, remains a constant value if no significant change takes place in the spanwise weight distribution. The maneuvering speed of the subject aircraft of Figure 5.4 would be VA equals 100 times the square root of 7.5, or VA equals 274 knots. Effect of high-speed flight. Many different factors may be of structural importance in high-speed flight. Any one or combination of these factors may be encountered if the airplane is operated beyond the limit, or redline, airspeed. At speeds beyond the limit speed, the airplane may encounter a critical gust. This is especially true of a high aspect ratio airplane with a low limit load factor. Of course, this is also an important consideration for an airplane with a high limit load factor if the gust should be superimposed on a maneuver. Since the gust load factor increment varies directly with airspeed and gust intensity, high airspeeds must be avoided in turbulent conditions. When it is impossible to avoid turbulent conditions, and the airplane must be subject to gusts, the flight condition must be properly controlled to minimize the effect of turbulence. If possible, the airplane airspeed and power should be adjusted prior to entry into turbulence to provide a stabilized attitude. Obviously, penetration of turbulence should not be accomplished at an excess airspeed because of possible structural damage. On the other hand, an excessively low speed should not be chosen to penetrate turbulence, for the gust may cause stalling of the aircraft and difficulty of control. To select a proper penetration airspeed, the speed should not be excessively high or low. The two extremes must be tempered. The maneuvering speed is an important reference point, since it is the highest speed that can be taken to alleviate stall due to gust, and the lowest speed at which limit load factor can be developed aerodynamically. The optimum penetration speed occurs at or very near the maneuvering speed. Aileron reversal is a phenomenon particular to high-speed flight. When in flight at very high dynamic pressures, the wing torsional deflections which occur with aileron deflection are considerable and cause noticeable change in aileron effectiveness. The deflection of an aileron on a rigid wing creates a change in lift and produces a rolling moment. In addition, the deflection of the control surface creates a twisting moment on the wing. When the actual elastic wing is subject to this condition at high dynamic pressures, the twisting moment produces measurable twisting deformations which affect the rolling performance of the aircraft. Figure 5.5 illustrates this process, and the effect of airspeed on aileron effectiveness. At some high dynamic pressure, the twisting deformation will be great enough to nullify the effect on aileron deflection, and the aileron effectiveness will be zero. Since speeds above this point create rolling moments opposite to the direction controlled, this point is termed the aileron reversal speed. Operation beyond the reversal speed would create an obvious control difficulty. Also, the extremely large twisting moments which produce loss of aileron effectiveness create large twisting moments capable of structural damage. In order to prevent loss of aileron effectiveness at high airspeeds, the wing must have high torsional stiffness. This may be a feature difficult to accomplish in a wing of very thin section and may favor the use of inboard ailerons to reduce the twisted span length and effectively increase torsional stiffness. The use of spoilers for lateral control minimizes the twisting moments and alleviates the reversal problem. Divergence is another phenomenon common to flight at high dynamic pressures. Like aileron reversal, it is an effect due to the interaction of aerodynamic forces and elastic deflections of the structure. However, it differs from aileron reversal in that it is a violent instability which produces immediate failure. Figure 5.5 illustrates the process of instability. If the surface is above the divergent speed, any disturbance precipitates this sequence. Any change in lift takes place at the aerodynamic center of the section. The change in lift ahead of the elastic axis produces a twisting moment and a consequent twisting deflection. The change in angle of attack creates greater lift at the AC, greater twisting deflection, more lift, etc., until failure occurs. At low flight speeds where the dynamic pressure is low, the relationship between aerodynamic force buildup and torsional deflection is stable. However, the change in lift per angle of attack is proportional to v squared, but the structural torsional stiffness of the wing remains constant. This relationship implies that at some high speed, the aerodynamic force buildup may overpower the resisting torsional stiffness, and divergence will occur. The divergent speed of the surfaces must be sufficiently high that the airplane does not encounter this phenomenon within the normal operating envelope. Sweepback, short span, and high taper help raise the divergent speed. Flutter involves aerodynamic forces, inertia forces, and the elastic properties of a surface. The distribution of mass and stiffness in a structure determines certain natural frequencies and modes of vibration. If the structure is subject to a forcing frequency near these natural frequencies, a resonant condition can result with an unstable oscillation. The aircraft is subject to many aerodynamic excitations while in operation, and the natural modes must be damped if possible or designed to occur beyond the limit speed. A typical flutter mode is illustrated in Figure 5.5. Since the problem is one of high-speed flight, it is generally desirable to have very high natural frequencies and flutter speeds well above the normal operating speeds. Any change of stiffness or mass distribution will alter the modes and frequencies, and thus allow a change in the flutter speeds. If the aircraft is not properly maintained, and excessive play and flexibility exist, flutter could occur at flight speeds below the limit airspeed. Compressibility problems may define the limit airspeed for an airplane in terms of Mach number. The supersonic airplane may experience a great decay of stability at some high Mach number or encounter critical structural or engine inlet temperatures due to aerodynamic heating. The transonic airplane at an excessive speed may encounter a variety of stability, control, or buffet problems associated with transonic flight. Since the equivalent airspeed for a given Mach number decreases with altitude, the magnitude of compressibility effects at high altitude may be negligible for the transonic airplane. In this sense, the airplane may not be able to fly at high enough dynamic pressures within a certain range of Mach numbers to create any significant stability or control problem. The transonic airplane which is buffet limited requires due consideration of the effect of load factor on the onset of buffet. Since critical Mach number decreases with lift coefficient, the limit Mach number will decrease with load factor. If the airplane is subject to prolonged or repeated buffet for which it was not designed, structural fatigue will be the certain result. The limit airspeed for each type aircraft is set sufficiently high that full intended application of the aircraft should be possible. Each of the factors mentioned about the effect of excess airspeed should provide due respect for the limit airspeed. Landing and ground loads. The most critical loads on the landing gear occur at high gross weight and high rate of descent at touchdown. Since the landing gear has requirements of static strength and fatigue strength similar to any other component, overstress must be avoided to prevent failure and derive the anticipated service life from the components. The most significant function of the landing gear is to absorb the vertical energy of the aircraft at touchdown. An aircraft at a given weight and rate of descent at touchdown has a certain kinetic energy which must be dissipated in the shock absorbers of the landing gear. If the energy were not absorbed at touchdown, the aircraft would bounce along similar to an automobile with faulty shock absorbers. As the strut deflects on touchdown, oil is forced through an orifice at high velocity, and the energy of the aircraft is absorbed. To have an efficient strut, the orifice size must be controlled with a tapered pin to absorb the energy with the most uniform force on the strut. The vertical landing loads resulting at touchdown can be simplified to an extent by assuming the action of the strut to produce a uniformly accelerated motion of the aircraft. The landing load factor for touchdown at a constant rate of descent can be expressed by the following equation. Lowercase n equals F over W. Lowercase n equals ROD squared over 2g times capital S. Where lowercase n equals landing load factor, the ratio of the load in the strut, F, to the weight, W, ROD, equals rate of descent due to gravity, or ROD, equals rate of descent in feet per second, G, equals acceleration due to gravity, or G, equals 32 feet per second squared, and capital S, equals effective stroke of the strut in feet. As an example, assume that an aircraft touches down at a constant rate of descent of 18 feet per second, and the effective stroke of the strut is 18 inches, 1.5 feet. The landing load factor for the condition would be 3.37, the average force would be 3.37 times the weight of the aircraft. Note: there is no specific correlation between the landing load factor and the indication of a cockpit-mounted flight accelerometer. The response of the instrument, its mounting, and the onset of landing loads usually prevent direct correlation. This simplified equation points out two important facts. The effective stroke of the strut should be large to minimize the loads, since a greater distance of travel reduces the force necessary to do the work of arresting the vertical descent of the aircraft. This should emphasize the necessity of proper maintenance of the struts. An additional fact illustrated is that the landing load factor varies as the square of the touchdown rate of descent. Therefore, a 20% higher rate of descent increases the landing load factor 44%. This fact should emphasize the need for proper landing technique to prevent a hard landing and overstress of the landing gear components and associated structure. The effect of landing gross weight is twofold. A higher gross weight at some landing load factor produces a higher force in the landing gear. The higher gross weight requires a higher approach speed and, if the same glide path is used, a higher rate of descent results. In addition to the principal vertical loads on the landing gear, there are varied side loads, will spin up and spring back loads, etc., all of which tend to be more critical at high gross weight, high touchdown ground speed, and high rate of descent. The function of the landing gear as a shock-absorbing device has an important application when a forced landing must be accomplished on an unprepared surface. If the terrain is rough, and the landing gear is not extended, initial contact will be made with relatively solid structure, and whatever energy is absorbed will be accompanied by high vertical accelerations. These high vertical accelerations encountered with a gear-up landing on an unprepared surface are the source of a very incapacitating type injury, vertical compression fracture of the vertebrae. Unless some peculiarity of the configuration makes it inadvisable, it is generally recommended that the landing gear be down for a forced landing on an unprepared surface. Note: for those prone to forget, it is also recommended that the gear be down for landing on prepared surfaces. Effect of overstress on service life. Accumulated periods of overstress can create a very detrimental effect on the useful service life of any structural component. This fact is certain and irreversible. Thus, the operation of the airplane, power plant, and various systems must be limited to design values to prevent failure or excessive maintenance costs early in the anticipated service life. The operating limitations presented in the handbook must be adhered to in a very strict fashion. In many cases of modern aircraft structures, it is very difficult to appreciate the effect of a moderate overstress. This feature is due in great part to the inherent strength of the materials used in modern aircraft construction. As a general airframe static strength requirement, the primary structure must not experience objectionable permanent deformation at limit load or failure at 150% of limit load. Ultimate load is 1.5 times limit load. To satisfy each part of the requirement, limit load must not exceed the yield stress, and ultimate load must not exceed the ultimate stress capability of the parts. Many of the high-strength materials used in aircraft construction have stress-strain diagrams typical of Figure 5.6. One feature of these materials is that the yield point is at some stress much greater than 2/3 of the ultimate stress. Thus, the critical design condition is the ultimate load. If 150% of limit load corresponds to ultimate stress of the material, 100% of limit load corresponds to a stress much lower than the yield stress. Because of the inherent properties of the high-strength material, and the ultimate factor of safety of 1.5, the limit load condition is rarely the critical design point and usually possesses a large positive margin of static strength. This fact alone implies that the structure must be grossly overstressed to produce damage easily visible to the naked eye. This lack of immediate visible damage with overstress makes it quite difficult to recognize or appreciate the long-range effect. A reference point provided on the stress-strain diagram of Figure 5.6 is a stress termed the endurance limit. If the operating cyclic stresses never exceed this endurance limit, an infinite, or in some cases, near infinite, number of cycles can be withstood without fatigue failure. No significant fatigue damage accrues from stresses below the endurance limit, but the value of this endurance limit is approximately 30 to 50% of the yield strength for the light alloys used in aircraft construction. The rate of fatigue damage caused by stresses only slightly above the endurance limit is insignificant. Even stresses near the limit load do not cause a significant accumulation of fatigue damage if the frequency of application is reasonable and within the intended mission requirement. However, stresses above the limit load and especially stresses well above the limit load create a very rapid rate of fatigue damage. A puzzling situation then exists. Overstress is difficult to recognize because of the inherent high yield strength and low ductility of typical aircraft metals. These same overstresses cause high rate of fatigue damage and create premature failure of parts in service. The effect of accumulated overstress is the formation and propagation of fatigue cracks. While it is sure that a fatigue crack will always be formed before final failure of a part, accumulated overstress is most severe and fatigue-provoking at the inevitable stress concentrations. Hence, disassembly and detailed inspection is both costly and time-consuming. To prevent in-service failures of a basically sound structure, the part must be properly maintained and operated within the design envelope. Examples of in-service fatigue failures are shown in Figure 5.7. The operation of any aircraft and power plant must be conducted within the operating limitations prescribed in the flight handbook. No hearsay or rumors can be substituted for the accepted data presented in the aircraft handbook. All of the various static strength, service life, and aeroelastic effects must be given proper respect. An airplane can be overstressed with the possibility that no immediate damage is apparent. A power plant may be operated past the specified time, speed, or temperature limits without immediate apparent damage. In each case, the cumulative effect will tell at some later time when in-service failures occur, and maintenance costs increase.